me for one more quantum number. It's called the magnetic quantum number. It is lowercase m subscript L. So m sub L. The magnetic quantum number defines the orientation of individual orbitals within a subshell. Okay? So orientation is the direction that something is sitting, okay? Which way it's pointed, essentially. Okay? And look at how this works out. The possible values for m sub L are integers of negative L to positive L. Okay? So again, that depends on which L, that depends on which orbital shape we're talking about. Okay? And we count integers negative to positive from that. So let's take our table from the last page. N equals 1, L equals 0. That's 1s. That's a spherical, okay, orbital. To get the magnetic quantum number, we go from negative 0 to positive 0, which is just 0. Okay, that's our only choice. You can write 0 only there. And that's why there is just one orbital. Okay? If L equals 0, it's spherical, and there's only one of them. Why do you suppose there aren't different spheres that point in different directions? Can a sphere point in different directions? No. A sphere is a sphere. Okay? A sphere can't point in any directions. A sphere is just a sphere. So any S subshell contains just only that particular orbital, okay? And that's it. Just that particular shape, and no extra copies of it pointing in different directions. Okay? So same thing with 2s. That's a sphere. It's just a bigger sphere. Okay? So 0 only one orbital. Okay? Spheres can't point different directions. Okay. Then we get to 2p. Okay. Tell me again what shape a p orbital is.
2 lobes.
2 lobes. Okay. So looks like that. Okay. L is 1. So now we've got 3 choices for the magnetic quantum number. We've got negative 1, 0, and positive 1, because that was sort of our definition, possible values for m sub L. Okay. So we can have a negative 1, a 0, and a positive 1. All that tells us is that there are 3 different orbitals, okay, for any p type, like that. And since a p orbital could be just centered on one axis, like that, the directions of those p orbitals, one of them would be left-right, one of them would be front-back, and one of them would be up-down. It's the x and y and z of the 3-coordinate axis system, right? So okay. I know that's x. I'll make z the front-back one. Doesn't matter. But those are the 3 directions of a coordinate axis system. Okay. I'm going to show you some better pictures of these in a second. But any p subshell like that will have 3 different p orbitals, okay, that are different by their direction. Okay. One will be on the x-axis, one will be on the y-axis, one will be on the z-axis. Okay. So let's keep going. How many different n equals 3 subshells are there? Yeah. There's 0, 1, and 2. Look at how that works. How many different n equals 1 subshells are there? Well, there's just one. How many different n equals 2 subshells are there? There's 2, okay? So every shell will have n subshells, okay? Because it goes from 0 to 1 minus n, essentially, okay? So that means there are going to be 3 subshells in n equals 3. There are going to be 4 in n equals 4, 0, 1, 2, and 3. There are going to be 5 possible ones in n equals 5, and 6 possible ones, and so on. We won't write all those, thank God. Okay, so 3s, 3p, 3d, 4s, 4p, 4d, 4f. Okay? So 3s defines a particular orbital size and shape. Okay? S means it's spherical, 3 means it's bigger than 2, right? What are the possible values for this magnetic quantum number, though? Just 0. Okay? Because it's a sphere can only point one way. Okay? So there's only one spherical orbital. Possible values for these 3p orbitals will be the same as up here, right? Because we're going to go from negative this all the way through positive this. So we're going to go negative 1, 0, and plus 1. So again, there are 3 of them. Okay? There'll be one on the x, one on the y, one on the z. How many 3d orbitals will there be in a set then? 5, because we can go negative 2 all the way up to positive 2. There are 5 of them. Okay? And you could repeat the same pattern for these s's, but how many f orbitals will there be? There will be 7 of them in a set, because we'll go from negative 3, 2, 1, 0, 1, 2, 3. Okay, so let's summarize. Subshell, number of orbitals. If we're in an S, that's spherical, and a sphere only points one way. Okay. P, how many?
3.
3. D? 5. F? 7. Okay. So, number or orbitals, number of orbitals. Okay. So, we said on the last page that these first 2 quantum numbers define a subshell. Well, we need the first 3 quantum numbers to define a particular orbital, because a subshell might contain a group of similar orbitals that are just in different directions, like that. Okay? So n, like we said, what does n tell us about an orbital? Energy and
Size.
Yep. Energy and size. Okay. What does L tell us about an orbital? Shape. There's also a slight change in energy, too. That will be important to us in a minute, or next time. Okay. What does M sub L tell us about one particular orbital within a group? Orientation or direction. But if only the orientation changes, those are all the same energy. In a subshell. Okay? So, I've got some pictures on the next page that'll illustrate this a little bit for us. Okay? Every S subshell, whether it's 1s, 2s, 3s, 4s, 5s, that's a single spherical orbital. Okay? And there's only one possibility for that, because rotating a sphere doesn't actually change the sphere, okay? Especially if it's just an area that you're talking about. Every p subshell has 3 dual-lobed orbitals. Okay? Px, they oriented their axes different. Okay? That's what a px looks like, and sometimes orbitals are shown as these little sort of foggy kind of areas, because you're just imagining the density of where an electron might spend most of its time. Okay? We're talking about probabilities, remember. Okay? So you might have an electron in a px orbital that's over here and over here a bit, a py orbital that occupies a different axis, and a pz orbital that occupies a third axis. All three of those orbitals are centered at the same place. They're all centered at the nucleus. And actually, the reason that there are three of them is because that's how we get a symmetrical distribution of these two-lobed areas in 3 dimensions, it turns out. Okay? So here, let's just write that. There are 3 orbitals in the same area. Okay. So here, I will attempt to draw a little picture of those. I'll use some different colors. Okay, so say we got one that axis, one coming forward, going back behind, some dotted lines there. One on the z-axis, like that. Okay, not bad. In yours, that's just going to be a jumble of little ovals. Okay, so understand, even though we showed them separately there, they're actually occupying the same central space. Okay, even though they kind of sit, they don't really overlap very much. Okay, they each sort of occupy their own space within the orbitals. And this whole thing, use my orange here, this whole thing is a p subshell. Okay. And the quantum number that tells these apart is that magnetic quantum number, ml equals -1, ml 0, +1. Right? But otherwise, within that group, they would have the same n and l, because n and l define a subshell. Okay? So a subshell can have multiple orbitals in it, but those orbitals are just going in different directions. Go ahead.
And there's just one electron per orbital?
Not necessarily. Up to 2, but we'll get to that next time. D, these are the Ds. Every D subshell has 5 orbitals. Okay? 3 of them come from being centered on the 3 coordinate axes. Okay? 1 of them is centered on one axis but shifted. And then check out this 5th one. It's got 2 lobes and sort of a little hula hoop around the middle there. So it's a bizarre kind of thing. But again, like I said, a mathematician wouldn't think that was funny at all, because that's the way that we have a certain number of nodes spread out symmetrically in 3 dimensions. It's just sort of mathematically how it is. And this one here that's rotated is on the perpendicular axis to the funny one. That's sort of how that works. But that's how we get essentially 5 different equal spaces that are symmetrical in 3 dimensions. Yeah.
Wouldn't that mean the hula hoop is crossing the other?
Yeah, they can. Yeah, they can overlap. It's not that they can't overlap. The p orbitals really don't overlap very much, but 2 of these d orbitals overlap pretty well. Not even that much. This one and that one are. It's hard to see from this angle, but they're rotated 45 degrees. Okay, so not too much overlap here. And then since there's a node in the middle, that little hula hoop sort of takes up a good amount of the space of that node in the middle that both of those ones took. And then there's nothing right on the z-axis itself, so that's where those ones come from. So it's really interesting and kind of bizarre, and I honestly really don't get why why it's shaped that way, but I trust the mathematicians, and that's That's really the way that 5 things spread themselves out in space with a certain number of nodes. Okay? That's not just the way 5 little groups space themselves out. We'll talk about molecular geometries later. But with an increasing number of nodes, sort of thinking the 3-dimensional version of the jump rope going up and down, that's actually what it starts to look like. Okay? So, I'm going to just continue on this one page right here because it's going to be a really nice introduction, and I'll tell you the 4th of the quantum numbers. So all we've been talking about up till now has been leading us up to being able to write an electron configuration, which essentially is just saying where all the electrons are, what type of orbitals all of the electrons in an atom are in, and then how many electrons are occupied within those orbitals. So we've discussed the ground state a little bit for hydrogen. The ground state for hydrogen is easy because there's one electron and it's in its lowest energy state. Okay? But if we have multiple electrons, it's the lowest energy, most stable state for an atom that has all the electrons in the lowest energy possible orbitals. But if we've got 20 electrons, they're not all going to crowd into 1s, the first orbital. Okay? There are rules for occupancy, for how many electrons will fit in particular orbitals that we're going to go through next time. Okay? But let's start with H. The energy of an electron in an H atom depends only on the principal quantum number n. So in its ground state, the electron will occupy what is the lowest energy orbital type. Yep, it's n equals 1. And what's the only kind of shape that n equals 1 has? Yeah, spherical, okay, 1s. So the electron of an H atom in its ground state occupies a 1s orbital, and we would write that electron configuration like this, 1s, and we put a little superscript 1 there, because that's just saying the number of electrons in that subshell. In any of the orbitals that are 1s in type. Okay? And an orbital diagram is just a figure that organizes electrons in their orbitals. We're going to draw a box to represent an orbital, and an arrow in that box is an electron. So that one electron in the 1s orbital will be just an up arrow, and draw an arrow with just one little spike on the side, like that. Okay? That is one electron in a 1s orbital. Okay? And the reason we drew that as an up arrow, like that, is because the final quantum number that we'll deal with deals with the electron spin. Spin is the direction of an electron's inherent angular momentum. So every electron has a little magnetic field around it, just like a spinning magnet or something would have a magnetic field that it creates. Okay? And electrons, they aren't actually spinning, but they create a magnetic field as if they were spinning. And spin is inherent to particular electrons. Okay? An electron will have up spin or down spin. And it's weird thinking about directions because it doesn't matter what you turn, but it's just something, it's a property of an electron that can be either one thing or the other thing. Okay? It's kind of like a light bulb switching on or off or something. There are only 2 states to it. Okay? So we refer to that as up spin and down spin. Okay? And that's the last quantum number. And that one's really easy. That can only be plus 1/2 or minus 1/2. Okay? So if this electron was an up spin electron, we would also be able to fit another electron in that same orbital, but its spin would probably have to be what? Spin would have to be down so that it's not repelling from that original one. Okay? So that's why we can fit 2 electrons into any one orbital. If one is up spin and one is down spin, then they can coexist in exactly the same space. Okay? So that's where we're going to pick up next time. We're going to start writing electron configurations. We will be able to write any electron configuration by the end of next time, but with a good understanding about what it is we're actually talking about. So we will see you then.
It's still okay. I make up last week's lab today. I couldn't take the pre-lab quiz
Oh, okay.
this morning. Also, my lab book might be in my car, but it
Um,
might be at home because I was in a hurry and
okay.
I've forgotten it. But
Well,
I
you
can
can-
copy some stuff
yeah.
onto paper. And
Yeah, you can copy it down. Did you grab your exam? Here, grab it.
My dogs got together and they ran away.
Jeez.
Awesome, thanks.
There you go.